So our next topic is, one-dimensional systems. There's a lot to be learned from one-dimensional systems. Why one-dimensional system? Our world is not one-dimensional. But, with symmetry, a lot of systems are one-dimensional. And also, for example, if you have a spherical symmetry, then the only dimension that matters is the radial dimension, right? So effectively, it becomes one-dimensional, right? And then if you have cylindrical symmetry, that is also one-dimensional because it's rotationally invariant in the two-dimensional plane, and also often it is also translationally invariant in the z direction. Okay, so one-dimensional system can be often solved exactly. Often should be taken with a touch of salt. It's actually very unrealistic potentials, such as step potentials, which can be often exactly solved exactly. But at least we can program computers to deal with them very, very easily. Okay, so the intuition that we gather from 1D systems, is very important. Okay. So without further ado, let's deal with the simplest one-dimensional system, which is a particle in a box. Okay, so as I said before, what is it? Okay, first of all, what is a particle in a box? Okay, so suppose that we have a box with impenetrable walls. Okay, so we have a box, and these walls are impenetrable. So the one-dimensional version of this, so the 1D version of this can be represented by a potential, say V of x, such that the potential is 0 if the modulus of x is less than L/2, and it's infinite if the modulus of x is greater or equal to L/2. In other words, suppose that this is my x, and this is the v-axis, v of x, and here we have minus L/2, and here we have plus L/2. And what happens is that there is no potential in between. This place is 0. But as soon as we hit L equals 2, x equals to L/2, the potential becomes infinitely high. Okay. Similarly, whenever we hit, this potential goes all the way up there. Okay. So if we have a particle inside, a quantum particle, then because it'll require infinite amount of energy to overcome the potential, it is confined to be inside this box, right? So this is this is known as the particle in the box. Okay. So this is more of a warming up exercise. I will do we'll start with a more of a formal analysis of the one-dimensional system in the next lecture. But today I just wanted to kind of give you more of a flavor of the kind of stuff that we are expecting. Okay. All right. So before we delve into the, into the analysis of the Schrodinger equation for this case, let me just also, note that what we want to do is that we want to solve the time independent Schrodinger equation. In other words, we want to find the energy eigenvalues and the eigenfunctions. Because if I have the energy eigenvalues, say psi of x, then we can just say, we can just append this factor to that, and then we find the time-dependent solutions, right? So if we can find this, we have all kinds of solutions, time independent, all the time dependent solution for free. Okay. So what is a time independent Schrodinger equation? Well, it's given by minus h squared by 2m d squared psi dx squared. So this is basically the kinetic term, and the potential term, we can write it on the other side. So this is the time independent Schrodinger equation in 1D. Okay. So we can also write this as d squared psi dx squared is equal to minus 2m e minus v over h bar squared times psi. Okay? Of course, v depends on x. Now, for realistic systems, v of x will be, will be a continuous function of x, right? But we idealize certain systems, and we allow for, we idealize systems, such as the particle in a box is such an idealization. We idealize systems and allow for potentials to be discontinuous. Okay? Okay. So if I allow such potential to be discontinuous, what happens is that, the right-hand side, this thing, is going to be a discontinuous function, right? If this is a discontinuous function, then we have to allow d squared psi of dx2 squared, dx squared to be, we allow this to be discontinuous as well, right? But in such cases, but in such cases, d of psi of d of x is continuous. Right? So this is essentially if it's discontinuous, but with a finite discontinuity. Right? And I just visualize this. Suppose we have some discontinuity, which is kind of finite, say, right? So our potential, so this is on this side, say this is the second derivative of psi, and on this side, this is the second derivative of psi. So this is a discontinuous, this is a discontinuous function. But the first integral of this guy is going to tell me that, it's going to be, I don't know, something like this, right? So this has some positive value, and say this has some, it should be probably the other way around, right? Yeah, something like this, right? So for if the second derivative has a finite discontinuity, then this thing is continuous. It's not differentiable, but it's continuous, okay? But if the second derivative of psi has an infinite discontinuity, as we do in the particle in a box, has an infinite, i.e. large, discontinuity, then d psi by dx will have will be discontinuous, but psi itself will be continuous. Okay. It won't be differentiable, but it will be continuous. Do you guys follow what I'm trying to say here?